The man, Isaac Newton, was one of the frontliners in physics, especially classical physics, in areas dealing with motion. And we can't talk about motion or why things move without referencing Isaac Newton. And his major contribution was the proponent of three laws that govern motion. And this brings us to our topic today, linear momentum. You're welcome to Redicon Online Learning, and I still remain your favorite tutor support. If you're just joining for the first time, do well to subscribe to this channel and like and share this tutorial video to as many of your friends out there. All right, so you're going to talk about the Isaac Newton's the three laws of motion and the formulas associated with them. Now, next class, we'll be talking about collision, elastic and inelastic collision. And we are going to be solving past questions on them. So do well to subscribe to this channel so that you don't miss out. All right. Now, we are going to take these three laws. Okay, the first law, second law, and the third law, and we're going to give their mathematical expression and various applications of them. Now, the first law states that everybody or every object will continue in their state of rest or their state of motion in a straight line, except they were compelled to act otherwise by an external force. All right. For instance, this board is at rest; it is not moving, but an external force can make it to move. So until an external force acts on this board to move, it will remain in this state of rest. And the reluctance of a body at rest to move is called inertia, or the reluctance of a moving body to stop is called inertia. Okay, so a force must be overcome. A force must be overcome by another greater force. Okay, so we need to push the body to move by breaking that force of inertia. All right, so Isaac Newton was just saying that even though it is a moving body, as long as it is moving with a uniform velocity in a straight line, okay, and an external force comes and distorts it, it can stop it first. For instance, this is a road and we have a small car. I'm not so good at drawing, so you are going to bear with me. All right, this is another car, and this is a lorry coming. All right, so this lorry hits this car. This particular car was coming with speed and the lorry hits it, so the car stops suddenly. All right, so this force has stopped this moving vehicle from moving. So it was an external force that stopped it from moving. So that is what an application of the first law. Another application is when this car was moving, the other car comes from this way and changes its direction to this way. It is also an application of the first law. All right, so the second law states that the rate of change of momentum is directly proportional to the applied force and acts in the direction of the force. The rate of change of momentum. Now, what is momentum? Momentum is seen as the product of mass and velocity. That's momentum. So the rate of change of momentum is directly proportional to the applied force. That means force is directly proportional to change in momentum. Remember, I said momentum is mass times velocity. Okay, let's put it this way: change in momentum. This is a formula. This is the sign for change. Okay, momentum. All right. So I know that change means final minus initial. So if momentum is equal to mv, that means f is proportional to that's mv minus mu, where u is the initial velocity and v is the final velocity. And remember, the mass of the body is constant. Okay, so is that proportional to the rate of change? The rate of change means over time, right? So we're going to increase over t. All right, so we are going to introduce a constant of proportionality k. So f is equal to mv minus lu over t. But usually we don't add k. All right, we don't add k because we assume k to be 1. All right, so we have f equal to mv minus nu. We can factorize, making it n into v minus u. In the course of this video lesson, in case you don't understand anything, you can relate it to the comment section. We'll be able to answer you. All right, over t. So force is equal to this. All right. So, and guess what? In physics, acceleration is defined as the rate of change of velocity with time. Okay, and rate of change in velocity is final velocity minus initial velocity. Okay, and rate of change over t. So this is what acceleration. So we can put it here. So force is equal to ma. I guess this is very amazing because we'll be hearing that force is equal to mass times acceleration. So this is how we arrived at this particular formula for force. All right. So you can see it here. This is how we derived it. Okay. So the rate of change of momentum is directly proportional to the applied force, and it acts in the direction of this force. So that is Newton's second law of motion. Now, the third law is that action and reaction are equal and opposite. Imagine I give you a petty slap. What would be your reaction? Some of you slap me back. Some of you will start crying. So that crying, that slapping back is your reaction to my action. So physics explains it in this way, that to every action, there's an equal and opposite reaction. That means give me, I give you back. All right. So we have various application of this law. First of all, we have why working is possible. All right. The reason why working is possible is an application of this third law. Why working is possible. You know that when you walk, your first leg, or that's your right leg, is thrusts, while your left leg, the other leg, acts to balance the action of the first leg. Okay, that's why your leg is spread like this when you are walking. This is a thrust, and this one is balancing and it's coming along. Is an opposite and equal force to this. So why walking is possible is an explanation of the Newton's third law of motion. Are we together? Now, secondly, is the hammer and driven nail. Hammer and driven nail. All right, you have a nail. You want to nail this into the wall, and with your hammer you are hitting it inside. That hitting is an action. Now, the nail, remember, the nail is also going into the wall. Okay, it is the reaction. So the action is that there is a force that the hammer is coming with. All right, and the nail is also entering inside the wall. It's a reaction to the action of that force. All right. So 3, we have the recoil of a gun. The recoil of a gun. How many of you have shot a gun before? So you're going to see that we're going to pull the trigger. So pulling the trigger provides a force that sends the bullet out of the gun. All right. So you hear another sound, the recoil, which provides a backward force. And sometimes some new guys that don't know how to shoot a gun, this force can actually push you back because it comes with so much force. All right. So you can actually try to shoot a gun, but don't do this at home. Don't test it on a human being. Hey, please don't get a gun. A big one from Saboj. Then number 4, jet and rockets propulsion. Jet and rockets propulsion. How do jets and rockets, how do they move? Have you wondered why jets, how jets and rockets move? Why do they move? How do they move? It is because as they are moving, fuels are burning. All right, the burning of this fuel thrusts the jet or the rocket. This is a rocket. Don't mind my drawing, no man. Let's say this is a rocket. Elon Musk rocket. Okay, and this rocket is going up in the sky. So as it is going, the gases are burning. All right, it is thrusting the rockets upwards to move, it will move higher and higher. So as it is moving, remember, gases are being expelled from me. These gases are reaction. All right, so this provides a downward force that actually thrust the rocket upwards. So this is the reaction and this is the action. The moving up due to the boiling of this gas is the action. Why the downward expulsion of these gases, which thrust this up, is called what? The reaction. All right. So these are the various applications of the Newton's third law of motion. So as I said, in our next class, I'm going to be talking about collision. And collision is divided into two. We have the elastic and inelastic collision. So do well to subscribe to this channel so that whenever I drop that video, you'll be aware. Thank you and see you in the next class.